In the rectangular coordinate system, which you've seen forever because you've seen it in algebra, pre-calc, calculus, if you have a point, call it P, the coordinates X and Y are how you locate the point. You know, you go along the X-axis, X units, you go along the Y-axis, Y units, and then you draw, you know, imaginary vertical and horizontal lines, and you locate your point, and then you have this ordered pair, parentheses X comma Y. Fine. Well, in this other coordinate system, we're calling it polar, you can locate that very same point P. The same point P, but you don't have an X and Y axes. That's kind of not happening in the world of polar. What do you have? You do have, instead of the origin, it's the analog to the origin. They call it the pole. It's you can think of it as being 0, 0 because it is. But instead of X and Y coordinates, you have an R, which is like a directed distance. So if you make a line segment connecting your point P to the pole, that's the origin, R would be the distance away. And then the theta is the other coordinate, if you will. And it's the angle that the line segment OP makes with not the x-axis, because there's no such thing. You have something called the polar axis. The polar axis is kind of like a positive x-axis only. So you got an R, it's a distance, and you've got a theta, which is an angle. So here's a diagram that just shows you they're plotting some points. So the point right here, 2 pi thirds, is 2 units away from the pole. So you have these concentric circles to try to locate yourself. And it's making an angle of pi thirds with this polar axis. Now, you guys have seen graph paper for rectangular coordinate system. Graph paper typically looks like a bunch of little itty bitty squares, right? You've seen graph paper like that, I'm sure.
Yep.
Have you ever seen polar graph paper? Polar graph paper is not a bunch of little itty bitty squares. What it looks like is kind of like this. You'll see what looks like the X and Y axes, but you'll also see concentric circles building out like that. And polar graph paper is really cool, but it helps you graph stuff. So like this point down here, it's 3 units away from the pole, and it's making an angle of negative pi sixths with the polar axis. And then this is this, these points are the same, but they have 2 different representations. Oh, is that possible? Well, not in rectangular, but in polar, you can have that because representations are not unique. So this point with coordinates 3, negative pi sixths, is the very same point as 3, negative 11 pi sixths. Why? Because they're coterminal angles. You guys have seen that in trig, I'm sure. Now, let's try to get a relationship between rectangular and polar, because I need you to go back and forth between the 2 systems. So how do you get back and forth between rectangular and polar? We need conversion formulas to do that. So to get the conversions, first notice that if you've got your point xy, which is the same as the point r theta, so this is the polar coordinates, and this is rectangular, the r can be thought of as a hypotenuse of a right angle, a right triangle, if you look at your x and y as lengths and side legs of a right triangle. Here's a right triangle. And you guys know from trig, SOHCAHTOA. So one of the things that you should hopefully remember from your days, like if you wanted to find this x here and you already knew what r and theta were, you know that cosine theta is adjacent over hypotenuse from trig. Well, cosine of this theta would be x over r. And if you solve this for x, and that's pretty easy to do by multiplying both sides by r, you get a conversion formula that x is equal to r cos theta. Similarly, sine theta is opposite over hypotenuse. So for this right triangle, we'll have the y leg, that's your opposite. Your hypotenuse is r. And if you solve this equation for y, you'll get y is equal to r sine theta. So there's another conversion formula for you. And those are the conversion formulas you would use to get from polar to rectangular. But what if you needed to get from rectangular to polar? So you already knew what x and y are, but you needed to get the r and the theta. Well, if you use the Pythagorean theorem for this right triangle, x squared plus y squared has to equal the hypotenuse squared, which is r squared. So this is a conversion formula. Also, an alternative version of this is r is the square root of x squared plus y squared. Normally you'd say plus or minus, but we'll go with the plus. Now, what about the theta? Well, tangent theta is equal to opposite over adjacent. So what we can say is tangent theta is equal to y over x. So if you take tan inverse of both sides of this formula, you'll get that theta is equal to tan inverse of y over x. And you have to be careful because this formula only works perfectly in quadrants 1 and 4 only. Why? Let's do a little bit of review of arctan. This is good review for the final. Do you guys remember that from your days of arctan, the range of arctan x, which is the same as tan inverse, is negative pi halves to positive pi halves? Do you guys remember this?
Yes.
If you don't, you better. So if you have a point P that's located either in quadrant 1 or down here Q in quadrant 4, the formula here will work perfectly because, you know, the angles will be located here between negative pi halves and positive pi halves. But what if you had a point over here, call it R, that's over here in quadrant 2? So the angle, you know, would be something, I'm just making something up here, let's say 2 pi thirds, which is the correct angle. But that's not in the range of negative pi halves to positive pi halves, but you need it. You need it. What do? You're going to need to add 180 degrees or pi, if you're doing radians, if your point is in quadrants 2 and 3. Okay, that's a little tip for you. So let's do some plotting points and converting between rectangular and polar coordinate systems. You need to go back and forth. So if I give you polar coordinates, you give me the rectangular. If I give you rectangular, you got to give me polar. Okay? So it's not that hard. So the point 2, 2, this is rectangular. So 2, 2 is located right there. So we just plotted the point. Now it is in quadrant 1, which is good news. So that means if we do have to get the theta, the formula will work perfectly without any additions. So how do we get the r? Well, r is the square root of x squared plus y squared, which is square root of 2 squared plus 2 squared, square root of 4 plus 4, which is square root of 8. And if I simplify square root of 8, I get 2 square root of 2. So there's your r. And theta is tan inverse of y over x. Be careful, it's y over x, not x over y. So you got to be really careful there. Be careful. It's especially if you're taking a quiz or an exam, it's easy to screw that up and accidentally do x over y and then blow the whole thing. Does anybody remember what tan inverse of 1 is?
5/4.
Yeah, good job. So final answer here, 2 square root of 2 comma pi fourths is the ordered pair for polar. What does that mean exactly? It means that the distance of this point 2, 2 to the pole is 2 root 2, and the angle that line segment I just drew there is making with the positive x-axis is pi fourths. And it looks like it is true. So they want us to express the point in 2 other ways. So you're probably going to think I'm weird here, but what's another way of expressing pi fourths? Like if I had to give, what is this angle here going around the opposite direction? It's negative what? Negative something. What's that angle? Anybody know?
Negative 3 pi over 4.
You're on the right track. It's that. So these are equivalent. You know, they're just saying it's the same point. I prefer this one because it's easier to understand. I don't usually think about -7 pi force. Okay. Now, the one I'm about to write is probably going to annoy some of you, but it turns out it is possible for r to go negative. Really? Yeah. So I claim that -2 square root of 2, 5 pi fourths represents the same point. So in order for you to think about this a little bit, let's look at the angle first. Like if I went around and found 5 pi fourths, I think I'd be in quadrant 3. So 5 pi fourths is right there, right? 5 pi fourths. So I'm on this line right here, but I need to have I need my r to go in the opposite direction, and that's why we have -2 root 2, and that gets me back to the original point. So this is also equivalent to the original, not my personal favorite because it is kind of backwards to think about it, but it is equivalent. So the point I'm trying to make, I know this may be giving you a headache because it does give me a headache, to be honest, is that polar coordinates representation is not unique. Rectangular coordinates is unique. Like if I give you a point, 2, 3 in rectangular, there's no other way to represent that point. That's it, the point 2, 3. But in polar, you can have different versions and still be okay. All right, just so you know, it can get weird. So now let's do a point that's given to us in polar. So this is polar. So what does that mean? This is the r, and this right here is your theta. So they're giving you an r, and they're giving you a theta. Go get the x and y. They want you to convert to rectangular, so you want the x and the y. And this is pretty easy because x is equal to r cos theta. So for us, that's 4 cosine 5 pi 6. Uh-oh. What the heck is cosine 5 pi 6? Go look at your unit trig circle.
Negative square root of 3 over 2.
Perfect. Thanks, Alexa. You are absolutely correct. And reduce this to lowest terms. And I get -2 root 3. Okay. And then y is equal to r sine theta. That's the formula. And so then, oh no, what is sine of 5 pi 6? Okay, I think it's a half, and I get 2. So final answer, when I put this into ordered pair format, is -2 square root of 3, comma 2. Boom. Pretty easy, right? So how about you guys try one? You think you're up for it? How about you try 2? So you and a buddy are going to do examples 3 and 4. So when they say Cartesian, that's another fancy word for rectangular, just so you know. And they're giving you polar, and you have to convert to rectangular. So I'm going to put you in buddies. What the heck? Let's see. Hang on a second. Let me get these breakout rooms set up. Turn on your mic so you can talk to your buddies and go convert a couple of points for me. Good luck. Lizette, are you okay?
Yep.
Okay. Are you going to be typing in your answers?
Yeah, they worked out.
Okay. I just want to make sure you do, because you need to do that.
Yeah.
Okay.
I am.
All right. Just checking on you. Good deal. Okay. Welcome back, everybody. How did we do?
Right, wasn't too bad.
Wasn't too bad, right? It sure is easier than trying to do one of those power series problems, right? Okay, so hopefully that you were just plugging and chugging into the conversion formulas, because that's really all I wanted you to do. Just wanted you to get a little feel for it. So for example 3, since x is equal to r cos theta, and they gave you an r and a theta, what is 3 cos of pi thirds? That's pretty much all they were really asking you for. I think that's 3 times a half, which is 3 halves. So y is our sign. And this is where you get the those yucky radicals, but you know, you're gonna. So your final answer here, if you put in ordered pair format, and usually they want you to, is that. Everybody okay with that? Okay,
Yes.
so now I want to hear what you, who got the answer to example 4? What'd you get? I'll give you a hint. I want to hear ordered pair format. So what'd you get for this first guy here?
2.
2 is correct. Thank you. Yeah. And then what kind of theta did you get here? Okay. Is it pi thirds?
Negative pi thirds.
Negative pi thirds. Good. Now, why is that? Well, because they were doing theta is equal to tan inverse of negative square root of 3 over 1. And so what I do if I'm confused about, because this is weird, I don't have this memorized. I'll be honest with you. I'm like, I don't know. What the heck is that? So what I do is I whip out the graphing calculator and I make sure I'm in degrees mode, not radians mode, because radians, I mean, it's going to be some decimals. So I go into my mode and I get out of radians mode and I get to degrees mode, hit enter, and then do the second button and then to get the arctan. And then you want arctan of negative square root of 3. Ugh, yuck. Okay. And then I'm just going to hit enter. And so what you see there is the degrees, negative 60 degrees. Now, some books, and I'm not sure about Briggs, they'll let you get away with staying in degrees. But more often than not, they're going to want you to convert to radians. So negative pi thirds. Now, what's an also okay answer? What is coterminal with negative pi thirds that's just as good? So what's the positive version of negative pi thirds? You know, when you go down here, you get negative pi thirds. What if you went the positive way around?
5 pi.
5 pi thirds, right? Yeah, that's just as good. I'll take that. That's legit because that's coterminal. That's the same. So that answer should be just as nice. Okay, did anybody try example 5?
Professor, just a quick question.
Mhm.
Is it the same, is it equivalent to say -2, comma,
Ooh, you want to do the negative, huh? You're bold. You're bold. If you want to do the -2, then it would be you add pi to your negative pi thirds. You'd be over here.
pi thirds? Okay.
Yeah, it would be -2 positive pi thirds would be legit. But that's for people who like thinking backwards.
That's not me.
Yeah, okay. It's true. You're right. Yeah. Okay. Okay, how about this one? What quadrant is this in?
3. Third.
Yeah, if you plot -5 and then -2, you're going to be down here in quadrant 3, right? That's a red flag for me because I know that when they're going to ask me for polar, when I use my conversion formula for the angle, the regular one isn't going to work. This one here, I'm going to have to, I'll use my graphing calculator and I'll get something, but then I'll need to add 180 degrees to that answer to get the correct answer. Okay, just a little mental note. So back to the problem at hand. So here we are, they gave us the rectangular. So we have X and we have Y. So how to get R? Well, R is square root of X squared plus Y squared. So it's square root of the -5 squared plus the -2 squared, but that's square root of 25 plus 4, which is square root of 29, which is just a yucky number, but we'll leave it. Now the angle is the tangent inverse of y over x, so it's tan inverse of -2 over -5, but a negative over negative is positive, and I have no idea what this is. Like, ugh. So that's when I have my graphing calculator and I go, graphing calculator, what is tan inverse of 2 over 5? It's approximately 21.8 degrees. Okay, so approximately 21.8 degrees. Now, is that correct? Because look, I mean, if I connect this point to the pole, I hope you can see that this angle here, that is not negative, that is not equal to 21.8 degrees. The 21.8 degrees is in quadrant 1, right? And our point is located way the heck over here in quadrant 3. So what we need to do is we need to add 180 degrees to this, and then we'll have the right answer. So go back to your graphing calculator and go, okay, graphing calculator, I'm going to add 180 to this answer. Ah, that's the correct answer, 201.8. Okay, final answer here now when I rewrite it in ordered pair format, I will have square root of 29, and I'm not going to convert this to radians because it's just too weird. You can. You guys all know how to convert to radians, right? You would use the, if you're using stoichiometry here, 180 degrees is the same as pi. You'd multiply this and you would convert it to radians. I'm not going to do that though. Let's just leave it. So 201.8 degrees, roughly. All right. Any questions so far on converting points between rectangular and polar? Know how to do one to the other. It's not that hard. Now let's talk about polar graphs. This is fun. I love this topic. It's exciting because you get to use your graphing calculator again. So I hope you have it with you. Fire it up, people. Fire it up. I already taught you parametric equations last week, and you had to be in parametric mode rather, on your calculator in order to graph a set of parametric equations. Well, if you want to graph polar equations, you got to be in polar mode, baby. Yeah. So let's do polar graphs. Check it out. Let's graph r equals 3. Now, if I didn't have my graphing calculator, I could actually do this one by hand. What do you mean? It's the set of all points, every point, who is exactly 3 units away from the pole. Here's the pole. So exactly 3 units away, you know, roughly like right about here, that's 3 units away, 3 units away, 3 units away, 3, you know, I would just get a tape measure and I'd graph every single point that's 3 units away, and I would get a circle. That is a sad looking circle, but those are all the points that are exactly 3 units away from the pole. Now, graphing calculator is more fun, of course, and it's a little more pretty. So you go into mode and you tell the calculator that you want to graph in polar mode. So you go down to the same row that says function. And remember, we were in parametric mode, but now we want to go to polar. So have your cursor on top of the word polar. Click enter to make it happen. And then quit at it. Well, one other thing I want to do here, I'd like to go back to radians mode just because, and then quit out of here. Radians mode is good. Now go to y equals, and you're going to notice that the menu here has changed. It now says R1. You know, that's your R. So I'm going to hit my clear key. I don't know what I was doing before. Let's just graph R equals 3. Check my window. I want my theta min to be 0 and my theta max to be 2 pi because I want to go a full revolution, the full circle. When I hit graph, it doesn't look like a circle. Let me do zoom z square so you can see better. And let me do a zoom out too, because it looks kind of yucky. So there's my circle. Yay. And you see it's the set of all points that are 3 units away from the pole. Pretty cool, huh? Mm-hmm. This one, you cannot use your graphing calculator. Well, why not? You just told us we can use our graphing calculator to graph polar. I lied. The only equations that you can have to be written as r equals some function of theta, and this is not. Oh, well then how are we going to graph it? Well, this is kind of cheesy. Before I do this though, I forgot to do the other half of okay, your calculator didn't graph it, Roman. Did you make sure that you were in radians mode? Not only polar mode, but radians mode? Try that. Let me know how it goes. Okay, Roman? Get back to me on that one. Okay. I forgot to convert to rectangular on that last one. So let's do that. How do you convert to rectangular? So this time I'm not converting a point. I'm converting to an equation to an equation. So let me just write it over here. Here's my little scratch. R equals 3. Okay. So you use the conversion formula. Remember, R is the same as the square root of x squared plus y squared. So you substitute and then square both sides. And oh, do you guys recognize this rectangular equation? Do you guys recognize this equation as the equation for a circle of radius 3 centered at the origin?
Yes.
Yes.
Doesn't it match the graph? Yes? You need it to. Okay. So on this one, I can't use my graphing calculator. So how about if I convert to rectangular and then we'll just graph in func mode. So how do I convert this to rectangular? Well, this is a little bit tricky, but I'm going to take tangent of both sides of the equation. That seems kind of weird. I know. Now, tangent of pi fourths is a nice number. It's called 1. If you don't believe me, type it up in your calculator. Now, this side, if you look at our set of conversion formulas way back here on one of our first pages here, what we said about tangent theta up here, woo, too far, help, is that tangent theta is equal to y over x. That's good to know. Well, why? Because we're going to replace that left-hand side of the equation that says tan theta with y over x, and then solve this for y. Oh, y equals x. Oh, well, everybody knows how to graph y equals x. That's just a diagonal line, intercepts the origin, right? And we're done. And that is the graph of theta equals pi fourths. Now, you might argue, if you're a thinking student, well, wait a minute, this theta equals pi fourths should be all the points that are making an angle of pi fourths with the positive x-axis, like this. But these points over here look like they're making 5 pi fourths. Well, you can think of them as pi fourths with a negative r. So there you go, thinking backwards. Okay, let's do this one because it's kind of fun. You can use your graphing calculator now because it is written as a function of theta. So go to y of theta, hit your clear key, and then type in, what is this, 2 cos theta. Make sure you are in radians mode, otherwise it won't work. And it's a little itty bitty circle that's not centered at the origin. There it is. Kind of cute. Like it. So it's like that. Yeah, something more like that. So let's actually convert it to rectangular coordinates. Well, how do you do that? This one's hard. Watch closely. Now, when I teach trig, and I haven't taught trig for a while, but anytime I do teach trig, we do this because we cover polar in trigonometry class. So let's do a quick poll, quick break. Using the yes, no buttons, tell me if you recall covering polar when you took trigonometry, which is also pre-calc because you do trig in there. So yes, no. Do you recall doing any polar coordinates? Yes or no? Maybe not. Maybe you didn't get to it. No. 5 yeses, 6 no's so far. Keep voting. Anybody else? There's more people in the room. Some of you aren't voting. Are you guys even there, or did you go back to bed? Oh dear. The voting bar isn't working. That's probably because you use the Zoom link, not the Zoom app. Okay. It's no matter. It's not life or death. We'll get along. Okay. So when I cover polar, and if you didn't cover polar and trig, that's okay because we're doing it right now. Yeah. So we'll fill in the gaps for you. So the trick, here's the tricky poo, is multiply both sides by r. Now, normally that would be illegal in mathematics because how do you know r isn't 0? And multiplying both sides of an equation by 0 is not okay. Well, assume it isn't 0. Assume r is not equal to 0. Then it's legal. Then what? Well, then you'll have r squared is equal to 2r cos. How is that helpful? Well, now it's more easily converted. Why? Because r squared is the same as x squared plus y squared. And on the right-hand side, r cos theta is x. And we're done. That is the rectangular equation that is the same as this circle. Now, you could argue, well, this isn't helpful. That doesn't look like the equation of a circle to me. Well, if you did want to do a little extra here, I would move the 2x to the left-hand side of the equation, and then I would complete the square. And what do I mean? I would add a 1 here, and then whatever you add to one side of the equation, you have to also do to the other side to make it all okay. And then I would factor the perfect square trinomial. And this is a circle of radius 1, where the center point is 1, 0. Do you guys remember that from pre-calc, maybe? I don't know. Maybe. Okay. Let's do this one. This is hard. You're going to see this one in my lab math, so just pay attention because it's going to happen. Yeah. So how do you do it? You're going to use a trig identity first. What's the trig identity? Well, the double angle formula, sine of 2 theta. Does anybody remember what sine of 2 theta can be rewritten as? Nobody knows?
1 plus
Careful.
2. No.
Careful. You're thinking sine squared. Sine
Okay.
squared is this, which is true, but this is sine of 2 theta.
1/2 sine theta cos theta.
You're close. It's 2 sine theta cos theta. Yeah. So why is that helpful? Just go with it. Well, now what? Well, there's some tricks here. I'm going to divide both sides by cos and assume that cosine isn't 0 in order for me to do that. Okay. And now I'm going to use the trick that I just told you about before. Multiply both sides by r, and then use your conversion formulas, where r sine is the same as y. So x squared plus y squared equals 2y. And you're done. Now, if you were going to use your graphing calculator here, as long as you solve it for r, your graphing calculator can be used to graph it, because your graphing calculator requires r to be written as a function of theta. So we can do this without converting to rectangular. Here, I would just do sine 2 theta divided by cos theta, and then hit graph, and it's a circle that's not centered at the origin. Any questions so far? Zing. Okay. Now, the fun part about polar graphs is they're not just circles. You can have all sorts of fun stuff. So check out letter A and use your graphing calculator to do it, because it's fun. Clear key, 3 sine 4 theta. Hit it. Ooh, wow, that is so cool. That's called a rose curve. So look at all the petals there. Isn't that pretty?
It's really cool, actually.
When I was a kid growing up, we used to have a toy called Spirograph. It was very primitive. They'd give you sets of pens and plastic pieces that you would use to sketch stuff. But now kids just get an iPad. So I don't even know how I would graph this. Ding, 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 ding. Okay, there you go. It's a nice flower. How about 1 plus 2 cos theta? What's that look like? I don't know. Check it out. Clear. 1 plus 2 cos theta. Hit it. Oh, it's a loop-de-loop. Nice. It's a loop inside of a loop, basically. It's kind of cool. Letter C, r equals 1/2 theta. Oh, this is cool. Let me show you this one. Oh my God, I love this one. 1.5 theta. Before I do this one, what I want to show you is first have your window go from -10 to as a theta minimum, and then 0 is your theta max. Watch this. Do you see how it spiraled in? And then change your window where your theta min is 0 and your theta max is 10. And then look at the graph. Woo, it spiraled out. So if your window goes from -10 to +10, it's going to spiral in and then spiral back out. It's so cool. Woo! Look at that. Isn't that fun? If you're not impressed right now, I don't know what to say. While we're here, you know, like spiral in and then spiral out. I don't know how to draw it. What about r equals 1 minus, just for fun, try this one, 1 minus 2 cos, just for, you know, kicks and giggles. I don't know, something weird. Something weird. 1 minus 2 cos. Let's just try it. Let me clear this out. 1 minus. Let's just see what this one looks like. You never know. Oh, it's another one of those loop-de-loops. What about plus? What if I put a plus there? Will that be different? Let's see. Nope. What if I got rid of the 2 just for fun? I want to zoom in this one. See that? It's not really a circle. That's called a cardioid. I guess because it's kind of like, you know, a heart, sort of a heart, you know, like cardiovascular, heart, cardiology, the study of. Who said they wanted to be a medical doctor again? Jadalyn, was that you?
Yeah, I was about to raise my hand.
Okay, you're raising your hand right now. I'm not even seeing. Let me just see. Is there somebody else in the class right now that said that they are interested? I mean, their ultimate goal is to get into med school besides Jadalyn?
Me.
Me.
Jasmine. Okay, Jadalyn and Jasmine, the J's, J and J. Cool. Anybody else? I was just thinking about his cardio. Who said that? Who else?
Jose Andres.
Oh, Andres, you're going to med school also?
Yeah.
Okay, guys, I want to share something with you. Not yet. Let me get to it. I got an email the other day. Remember I told you, you may not appreciate me now, but in the future, send me some, emails to let me know how you're doing. I have a student of mine from a while ago. Like I think she had me for calculus 10 years ago. Okay. I know, right? And she wanted to get into med school, and she asked me many years ago to write her a recommendation letter to get into medical school. And she got into medical school. It was exciting stuff. Okay. And when she got in, she emailed me because she was so happy. And she wrote to me and I said, oh, congratulations. That's awesome. And then she recently just reached out to me again because she just graduated from med school and she's going to do her residency. Oh my God, I'm so excited for it. So crazy. So let me just share with everybody, even though I know not everybody in the room is excited to, hang on a second. I can't figure out how to do this. Oh, Zoom is so annoying. Okay, so here she is. Hope you're doing well. She wanted to reach out and share her graduation day is right around the corner. 17-year-old Julia had a dream she's going to become a doctor. 11 years later, that dream has become a reality. Seems like yesterday she was sitting in my calculus class at Southwestern College and asking for a letter of recommendation to support my medical school application. So she graduated from Western University of Health Sciences College of Osteopathic Medicine of the Pacific Northwest. And she did a whole bunch of other things. Looks like she started a program to help underrepresented minority backgrounds matriculate into MD and DO programs across the country. And it was a success. And she's graduating this Friday. And I can't go to her graduation. It's Zoom, but I got to proctor your exam. But she is going to do her residency in emergency medicine. Is that cool or what? We need more good doctors, people. So I just thought I'd share that with you because look, people that take me, they do survive, right? Eventually. Okay. So let's do the opposite, shall we? Let's do some rectangular equations, but then convert them to polar. And then we'll do derivatives in polar, and then we'll pretty much be done for today. And then Wednesday, we'll be doing a lot more calculus in polar. We're going to be doing area and arc length. Yeah, and that's all going to be on Friday's exam. Okay. So we're given a rectangular equation, convert it to polar. Now, if you had to graph this puppy, it's a circle, but it's not centered at the origin. You'd complete the square so you could see the center and the radius and all that, but I'm not going to go do that. I'm just going to immediately convert to polar. How? X squared plus Y squared is the same as what? Anybody remember?
R.
R².
Close.
R squared.
1.
Mhm. So you want to remember two things about R. X squared plus Y squared all by itself is R squared. That's the Pythagorean theorem. But if you just need R without being squared, it's the square root of X squared plus Y squared. So it's going to be R squared, and then you have minus 4Y. But what's Y? Look at the
R
conversion.
sine.
Good. R sine theta. Now, I'm not going to give you full credit for this. Well, but you said just go ahead and convert it. I know, but you need to try to clean it up if possible. Clean it up. Well, how do you do that? Add 4R sine theta to both sides. And we're trying to get it as a function of theta, if you can. And I'm going to do something normally illegal in math, divide both sides by a variable, but we're going to assume that R is not 0. So we'll just go with that. And this is our final answer. And you can use your graphing calculator to graph it. 4 sine theta, hit it. And it's a circle, but it's not centered at the origin. Let me do a zoom standard. That looks like an oval, but it's really a circle. So it looks like a circle where the center point is on the y-axis. So it's not centered at the origin. Okay. Okay. How about xy equals 4? Well, you could graph this if you solved it for y, and you would you'd get one of these puppies, right? 4 over x. But how would you convert to polar? Well, x is r cos theta, so substitute, and y is r sine theta, substitute, and that equals 4. But that's r squared cos theta sine theta equals 4. And they usually like, if you can, to try and solve it for r. So if I divide both sides by cos theta sine theta, and then square root both sides, and you should remember there is going to be a plus or minus, you'll get this. Now you could rewrite this a little bit. Square root of 4 is 2. And underneath the radical, if you rewrite the 1 over cos theta sine theta as 1 over cos theta times 1 over sine theta, and use some trig identities, 1 over cos is secant and 1 over sine is cosecant. So you could write it like that. So how would you graph it? Well, carefully, you would go, you know, to your, I'll just graph one of them. So I would graph like 2 square root of, ooh, I'm going to have to go like this. 1 divided by cos theta, and then times 1 divided by sine theta, like that. Let's see what happens. Ooh, that's pretty gross. Ah, we got part of it. Probably need to change my window. So I have, oh, theta min. How about -10 for theta min and +10 for theta max? I don't know. Let's see what happens. So it gives me the picture that looks like what we thought it would look like. Yay. How about y equals 5, which is just a horizontal line? Is that easily converted to polar? Sure. Just go r sine theta in place of y. That's the conversion formula for y. And then solve it for r. Oops, that's a 5, not a y. So r is equal to 5 over sine theta, which is 5 cosecant theta. Oops, cosecant theta. I can't write. Okay. And you can go graph that, and it should give you a straight line. Okay, so we're done with equations. So what's the point? Sorry, my heater's killing me over here. The point is, you may be asked to convert points from rectangular to polar, or a point from polar to rectangular. So those are points, ordered pairs. That's one type of conversion problem they'll ask you to do in the homework and on an exam. But then there's another kind of conversion, converting equations from polar coordinates to rectangular coordinates, or vice versa. So know the difference. You can convert points or equations. The thing that I've seen students mess up on is I'll give them an equation and I'll go, okay, this is in rectangular, convert it to polar coordinates. And they give me an ordered pair. I'm like, what the heck are you doing? I gave you an equation. So the answer has to also be an equation. Know the difference between converting points and converting equations. Don't get confused. That's the point. All right, now let's do derivatives. Okay, to be honest, this is pretty fakakta. Fakakta is Yiddish for messed up. Okay, so first up, some review. This is review right here. Really? Yeah. What do you mean? Well, remember parametric version of derivative? If you're confused with the theta, then we'll use the usual parameter t, but it's all the same, dummy variable or not. Remember that? You're actually going to use that for polar. Really? Yeah. Oh, man. Well, I don't get it. I thought we were in polar. Yeah. So it's going to turn out where to get the derivative in polar, you have to convert it to parametric and then use the parametric version. What? I told you it's pretty fakakta. Yeah, you're not going to like it because I don't like it. It's nasty. So here's the deal. You already know that the conversion formula from polar to rectangular is x is equal to r cos theta, and y is equal to r sine theta. So you're going to have to do that first. Then then what? Then since r is a function of theta, this r gets replaced whatever the function is. It's pretty gross. We're going to do some examples in case you're freaking out. Okay. So hang on for a second. Mm-hmm. Okay, so now you have to use the product rule, and this is where it gets messy. So if you were told that x is equal to the product of some weird function f of theta times cos, and they said go find the derivative, hold that thought for one quick second. Hold on a second. Okay, sorry about that. I'm trying to proctor an exam at the same time I'm doing this. So that's all I read. Okay, so if you're going to use the product rule on this, you're going to go f prime g plus g prime f. So you're going to go f prime times the other function, which is just cos, plus, what's the derivative of cos? Anybody know?
Negative sine theta.
Yeah, negative sine times just whatever the function is. So, and then adding a negative is really just the same as subtraction. So how about we rewrite this as subtraction? Okay, save this for later, but this is what you need to know. Your dx d theta has that look to it. And now using a similar thing, use the product rule on this to get dy d theta. You'll get f prime of theta times sine plus the derivative of sine, which is just cos, times your f of theta. Okay, so now what? Now you're going to put it all together. And this is where it's just, it's disgusting. But you're going to go dy dx is dy d theta divided by dx d theta, where dy d theta, we just did it, goes up top. And the dx d theta goes down here. And of course, provided the denominator doesn't equal 0, because that would be bad. Then you're going to have your derivative is undefined. That's probably where you have a sharp corner or a cusp or something like that. Okay, so the idea is if you have a polar graph, you know, maybe a spiral or something like that, and somebody picked a point and drew a tangent line to it, the slope of the tangent line would be equal to dy dx, which is this horrible looking thing, like awful, like bad. Okay. So we're going to do an example or two, and we're going to do it in slow motion just to kind of help ourselves out. Okay. Because it's kind of painful. I won't lie. So here's a lovely equation, and we'll graph it on the interval 0 to 2 pi, and just use your graphing calculator. These are fun. These polar graphs are just so cool. So what the heck does this guy look like? I don't know. Let's work it. 2, 1 minus sine theta. And check on my window. I want 0 as my theta minimum and 2 pi as my theta max. Okay, hit graph. What does it look like? Whoa, it's another one of those cardioids. Kind of looks like a heart, a circle heart, a heart circle. I don't know. You want to zoom in on it, make a better look at it. Woo! Yeah, it kind of looks like a little bit of a heart. Okay, fine. You want to graph. That looks pretty sad, but you get the idea. Okay, step 1, essentially, express x and y in terms of theta. Okay, x is equal to r cos, but r is 2 times 1 minus sine theta. So x is really this. Yeah, so save that for later. And then y, the conversion formula is r sine, but r, again, is that big old mess. So your y is 2 times, oops, parentheses, 1 minus sine theta, sine theta. Okay, so we just did part B. We're done. That's the first step to getting your dy dx. I know. Now, go get dy d theta and dx d theta. Okay, so let's do dy d theta first because they asked for it. You are going to need the product rule. So like, oh, how are you going to do this? Well, what I'm going to do is this big old factor, I'll call this f, and this factor I'll call g. So I'm going to go f prime g plus g prime f. This is the product rule in action. And, you know, on your final, I'm going to be putting one of these on there, and I'm basically looking to see if you know how to do your product rule. So it's kind of like a Calc 1 test, because that's where you learned how to do product rule, right? So if you look at this f, 2 times 1 minus sine theta, you could distribute the 2 first. Like, let's just do that so it's a little easier. There's your f. What is the derivative of 2 minus 2 sine theta?
-2 cosine theta.
So there's your f prime. Yay! And then times g, and I'll just copy down the g as sine theta, plus g prime. That's the derivative of sine. That's easy. That's cos times f. Ooh, the whole thing again. Okay, there's your hot mess. So there's dy d theta. I'm just going to leave it. You can clean it up if you want. Yeah, fine. Dx d theta. Product rule. So how about if we call this f and call this g, and you're going to go f prime g plus g prime f. Here we go. F prime, hey, we already did that. We know that's -2 cos times g, that's cos, plus g prime, negative sine, times f. Yeah, not pretty. Okay, and then put it all together. So your dy d theta is this big old mess here. And if you want, you can distribute and clean it up a little bit if you want to. I'm just gonna punch through it here. The only thing I'll do maybe is I'll put the 2 in front. Yeah, that's the ticket. That's a big mess. And then you've got the dx d theta. Okay. I could write that first term as -2 cos squared. Oh, I'll do that. And then I'll have -2 sine theta, parentheses 1 minus sine theta. Just leave it. Don't try to do any illegal canceling or anything like that. Okay, so you've got your dy d theta. Now what? Write the equation of the tangent line when theta is equal to pi. Oh, I knew they were going to make us do something like that. So before I do anything is I want to evaluate dy dx at theta equals pi, because that will give me the slope. So let's do that. So dy dx evaluated at theta equals pi. Oh boy, yeah, that's really exciting. So you're going to have -2 cos pi sine pi plus 2 cos pi, parentheses 1 minus sine pi. Now the good news is sine pi is a nice number. What is it? Anybody know? Sine pi equals what?
Zero.
Yeah. So that means that any of these terms that have a sine pi in it are going to just be, I can just cross it off. There's a 0. This thing is going to be 0 because sine pi is 0. And then this guy is 0. Now be careful, not everything cancels out. Don't get too excited here, okay? You got to be careful. What's still left here? We have 2 cos pi up top, and we have negative 2 cos squared pi down below, okay? Now cosine pi is a nice number. It's negative 1. And then when you square negative 1, well, it's 1. And so when I reduce this to lowest terms, oh my goodness, this doesn't always happen, but I get a 1. That's nice. Okay, now what? Well, I need the point, you know, the x coordinate and y coordinate. So how do I get that? So remember that we got x way up here. And we're going to plug theta equals pi into that to get the x coordinate of the point. And then y was this, and we'll plug theta equals pi to get the y coordinate. So to get the point is also kind of a hassle. So I'm just going to rewrite. X was 2 times 1 minus sine theta cos theta. So x evaluated at pi is 2, 1 minus sine pi cos pi. Okay, now sine pi is 0, but cos pi is negative 1. So you're going to have negative 1 times 2. And I get, for my x coordinate, negative 2. For the y, it was, I'll just copy it down again, 2, 1 minus sine theta. And if you plug in pi into your y, what do you think you're going to get here? Sine pi is 0. I get a 0.
0.
Cool. So the point that you're trying to find the tangent line to is at the point negative 2, 0 on the graph. Okay. So if you look at that heart that we graphed, I don't see negative 2, 0. We probably graphed it wrong. I imagine it maybe looks more like this. It's this point right here, negative 2, 0. We're trying to find that tangent line right there. Okay, and so look, we have all the ingredients. So I'm going to use my algebra point slope form. So y minus the y coordinate is equal to m, which is our slope, and x minus a minus 2 is x plus 2, and there's your equation of your tangent line. That's it. Any questions on that? I know that was pretty tedious, wasn't it? Don't worry, on the exam, I'm going to give you plenty of time to do it. So the last thing I'd like to do, and then I'm going to call it a day, and we're done with, well, I have a meme for you, but hang on. Let's do the points of vertical tangency. So what do I mean by vertical tangency? Well, dy dx is equal to undefined. When does that happen? That's your question. So if you look at the dy dx again, which was that horrible quotient, which is this, when does this when does this equal undefined is the question. When does a fraction equal undefined? You did this in Calc 1. Anybody remember?
Denominator equals 0.
Very good. Your denominator is 0. So this grand finale is I'm going to set the denominator equal to 0. So when is negative 2 cos squared theta minus, and I'm going to distribute that too, 2 minus 2 sine theta equals 0. When does that happen? Okay, now you got to whip out those trig chops to do this problem, because this is one of those hellacious trig equations that once you see it, you're going to go, oh, I do remember seeing that in my trig class. And that's when I said no. Really? Yeah. So what am I going to do here to do this problem? You'll see. All right. I'm going to clean it up a little bit. I'm going to distribute the minus and the sign. And so I'll have -2 cos squared -2 sine theta plus 2 sine squared theta. I think that's right. Equals 0. Yeah. Now don't go cos squared plus sine squared equals 1, because that ain't going to work, because these are subtracting. So this problem isn't going to be so easy. Unfortunately, what you're going to want to do is convert the cosines to sines. How? You're going to rewrite cos squared as 1 minus sine squared. And then you're going to have an equation with a bunch of sines in it, right? And it's actually a quadratic. So I'm going to clean up by distributing. And then I'm going to collect my like terms. What are my like terms? Well, look at this mess. I have a couple of terms that are both sine squareds. So when I combine 2 apples plus 2 apples, I add them together to get 4 apples. Yeah, that's right, 4 apples. Then what? Well, does that help? I'm going to just factor out a 2 and clean this a little bit by reducing this equation down a bit so it's not as ugly. And then divide both sides by 2 to kill off the 2. How does that help? It just gets me a little closer to being able to solve this trig equation. Now, here's the part where you're going to go, oh yeah, I remember doing this in trig, and it's giving me bad memories. I know. I'm getting bad memories too. I remember teaching trig back in '97 at Palomar during El Nino. You probably were born in the year 97. I don't know. We're going to use the method of substitution. Let u equal sine theta, and then you'll have a quadratic. And this factors, really? And the way I'm going to factor it is this thing here is what? -2u plus u minus 1. If I factor by grouping, I'm going to get 2u, but then that's u minus 1 plus 1, u minus 1. I think this is right. So I get 2u plus 1 times u minus 1. That's factored. Now what? Put the u back in. Okay, and then you're going to use the zero product property. If something times something equals 0, then you individually set the factors equal to 0. Okay, and then use your knowledge of trig. So I'm going to first subtract -1 here, and then I have sine theta equals -1/2. And then if I take inverse sine of both sides, I'll get theta equals, and you can use your calculator for this. Of course, there's multiple answers, but what's one, your calculator is going to give you, what's sine inverse of -1/2? Anybody know? I think it's -π/6. Yeah. And then this over here, if you add 1 to both sides and then take sine inverse of both sides, sine inverse of 1 is really easy because it's just π/2. Okay, so those are the points of vertical tangency. But the problem with these 2 points is it doesn't give you the point. It gives you what theta is doing. So what you're going to need to do is separately substitute into x and y to get the actual location rectangular. Which x and y? Well, you're not going to like this, but remember back here, we said x is f of theta cos theta. Whoops. You plug it in there, and then similarly, y looks like f of theta sine theta, and that will give you the actual points, rectangular points. Okay, I'm not going to complete on that. I'll just let you do it individually, but that's how you would get the position on a graph. All right, so it's a lot of work, and full disclosure, for those of you who are going to take Calc 3, we don't do half of this stuff in Polar that Calc 2 students are forced to do. Like, we never care about dy dx. ever. Okay, we just don't. But you do. Calc 2 people do. Well, what do you care about in polar? I like the conversion formulas. We do those. And we do arc, not arc length, but we do area, which we'll do on Wednesday. Okay. Any questions on this?
I got confused with the part.
The factor.
Okay. What part?
The factor by grouping.
The factor by grouping. Okay, I did it kind of quick, but I'll slow down a little bit. When you guys factor a trinomial, you might have some of your own tricks. Do some of you use, for example, the diamond method? Yes, no?
I've heard of it, or yeah, I've had it.
Okay. Well, I don't use the diamond method because I learned how to use it in 8th grade and I got really good at it, and now I forgot it. And I'm not as smart as I used to be when I was in 8th grade. So what I do instead is, first of all, I don't wish I was back in 8th grade though. I use what's called the key number method. So the key number for this trinomial is the lead coefficient, which is 2, times the constant, which is -1. So -2. Then I try to figure out all of the ways to factor the key number that the factoring, and 2 times -1 and -2 times +1 are the only two. But which one of these factorizations, when you sum the factors, add up to the middle coefficient? Well, the middle coefficient in this trinomial is -1. Yeah? So the correct factorization, or what I call the bingo numbers for me when I'm going to factor this guy are -2 and +1. So how do I use the bingo numbers? Well, what I do is I use the bingo numbers to rewrite the middle coefficient, or the middle term rather. The middle term was -u. And if I rewrite that by splitting it up into 2 pieces, would you agree that -u is the same as -2u plus +1u? Do you see how I use those bingo numbers of -2 and +1
Yes.
to split -u up into 2 terms? It's equivalent. But now I do the next trick, because I'm still not done factoring this polynomial, is I use factoring by grouping. And so I group the first 2 terms together as a pair, and then the last 2 terms I group together. And so what do I do when I group? Well, I look at the pair here, the first 2 terms. What is the greatest common factor between 2u squared and -2u?
The 2u.
Yes. And so when I factor out that pair's greatest common factor, which is 2u, the other factor will be u minus 1. Plus, then I look at the other 2 terms over here, which I've grouped together. And I go, okay, well, what's the GCF between those 2 guys? Well, there isn't anything. They don't have anything in common. Well, that's true, but you have to pull out something. Well, the only thing they have in common is 1. Okay, well, yeah, that's good. So factor out a 1, and then the other factor is u minus 1. And now you take a step back and you look at what you just did, and you notice that u minus 1 is common to both of these terms. So you can factor it out, and then the other factor is 2u plus 1. And then you have it. There is the factorization of that polynomial. Does that help?
Yeah, because I also saw that on the final study guide, and I was going to ask you about that, and you did it today anyway. So
Yeah,
thank you.
that's my personal favorite way of factoring a factorable, factoring over the set of integers, that is, trinomial. And it usually works nicely, unless you get a key number that's hellacious and has like 57 different ways of factoring. It can be kind of, it always gets you somewhere though. I prefer it to the trial and error method. That's just me. Okay.
Thank you.
You're welcome. Any other questions?